Okay, Module 6, let's get it done in 2 hours. Mod 6 is acid-base reactions. It's split into a few different inquiry questions, which all focus in on very specific conceptual ideas. Compared to Module 5, Mod 5 is quite conceptual with a little bit of calculation. Module 6 is once again a conceptual module with even more calculation than Module 6. So you have all that Ka, pKa, Kw scary stuff at the end. But before that, you have to build up all your understanding of acid base before you get onto those calculations, which is why the module is structured in sort of an introduction to acid and base, how acids and base react and interact in the second inquiry question. And finally, at the end, then you apply it all into these quantitative questions, which everyone dreads of in their trial in HSC. So we'll go from start to finish. We're going to cover what acids and bases are, what are their properties, how do you define an acid and base, the different definitions over the course of time. Acid-base reactions need to know what an indicator is, titration technique, explaining titration curves, so both the pH ones and conductometric, the different calculations, pH, pOH, Ka, Kb, pKa, pKb, Kw, and titration calculations, buffers, natural systems, and then industrial applications. We also will look at buffer calculations at the very end. Those are a more left of field type of question that you can get, important to cover. And then you'll also see the acid-base analysis techniques and everyday applications of acid bases. That's kind of the outline of what we're going to get through today in 2 hours. So if we go a little bit over, I do apologize, but there is a lot. In terms of how you should prepare for Mod 6, the main thing for this module is questions. There's nothing, it's similar to Module 2 in Year 11. So I just ran the intensive with the Year 11s. I was telling them that for calculations, the only way you're going to get better at calculations is by doing calculations. There is no point studying what Ka is, what pK is, and what they are after a period of time. You'll need to refresh those ideas. And the idea is after you leave this session today, you should be able to do every single Mod 6 question in theory. So when you leave the session after 2 hours a day, you have no excuse but to just do questions. And I promise you, the volume of questions you in Module 6 will directly reflect your mark similar to Module 2. You can't get away with cramming in the same way you can for something like Module 7. You can kind of cram a bit more, but 6 is very much applied. You need practice. You need to make mistakes in your practice and correct them as you go along. Okay, before I get started, does anyone have any questions? And the recording will be posted online like the Mod 5 one after it's finished, but it will take a few days. Okay, let's go. Inquiry question 1, properties of acids and bases. So we start off asking what is an acid, what is a base, and we talk about nomenclature and properties of acids and bases as the first sort of dot point. Investigate the correct IUPAC nomenclature and properties of common inorganic acids and bases. By now, we know that this definition provided here, which I give at the very start of this module, is now incorrect. This is not our full definition of what an acid is, nor is this the full definition of what a base is. Whose theory is this by? Someone shout it out. Whose theory are these definitions? Whose theory? Good, Ella. Arrhenius. So Arrhenius says that acids would dissociate to make hydrogen ions in aqueous solution. Bases would dissociate to make hydroxide ions in aqueous solution. So as you later find out in the module, this is not the best theory ever. There are limitations, and we improve on that with Bronsted, Lowry, and then Lewis theory after that. In terms of the essential acids and bases you need to know, hopefully you've seen most of these already. When we name acids, they tend to end in ic, and for the ones that are formed with halogens, like hydrochloric acid, hydrobromic, you have a hydrohaloic acid. For the other acids, you're basically forming acids, you're able to form acids with all your different polyatomic anions. So have a really good understanding of each anion, nitrate, acetate, sulfate, carbonate, phosphate, know their charge, know their formula, know their name. The one weird acid that everyone will get in their trial and have no idea is citric acid. Citric acid is C6H8O7, and I draw your attention to it because you need to know, is this a mono, di, or triprotic acid? Is this mono, di, or triprotic? Or octa? Can it do 8 hydrogens? So yes, tri. Citric acid is a triprotic acid. If you don't know that, there is no way you can figure it out in your exam. So it's an important case to remember. Citric acid is triprotic. On the base side of things, all of our bases, for the most part, will have hydroxide in them, but the important bases to remember otherwise are ammonia, carbonates, and also hydrogen carbonates can act as bases too. Okay, properties of acids and bases. Acids tend to have a sour taste, can burn skin, we call that corrosion. They're conductive in solution. What is conductivity? Someone unmute or type in chat. What is conductivity? Or electrical conductivity in this case. What makes something conductive?
It's like the measure to see if a solution can like conduct electricity. Probably not use conduct, but something like that.
Yes. So it would be whether a solution can conduct electricity, but what makes a solution able to conduct electricity? That's what I want to get into. And that question, we have to understand the answer is Ella, good, we're getting closer, and C has pretty much hit the nail on the head. High concentration of ions or mobile charge carriers. It basically means if something is conductive, electrically conductive, you have mobile charged particles. You have either ions or electrons, as Ella says, that can move around freely in solution and take charge from one side of the solution to the other. That is what it means to be conductive. If a solution has free moving charged particles, and that can either be electrons or it can be ions in solution. So is it electrons or ions in solution that makes an acid conductive? Electrons or ions in solution? What do acids have that make it conductive? Ions. Good. And the ions specifically typically are H+, and then the A- being the conjugate base, or for a base, they're also conductive because they have OH- and the conjugate acid. So understanding that's where conductivity comes from. It's from mobile charge carriers. Mobile charge carriers are what make solutions electrically conductive. And electrons are more related to like metals. When we said back in module 1, metals are conductive, that's because they have delocalized electrons, a C of them, that can move around freely from one side to the other of your metal. Acids and bases turn blue, litmus red. What is litmus? More than welcome to just unmute, makes things spell a little bit quicker. Indicator, perfect. So an indicator acts as a substance which can show change in pH for the purpose of module 6. So a pH indicator will show changes in pH through a color change. And blue litmus turning red shows an acidic solution, and red litmus turning blue shows a basic. So understanding that indicators tend to be red on their acidic side and blue on their basic side helps to understand where indicators usually would be. pH less than 7, pH greater than 7. What is pH? How do you define it? Type in chat. What is pH? How do we define pH? Concentration of hydrogen ions. Good. I like Josh's response. Negative log 10 of the concentration of hydrogen ions. This is what you say. If it's pH, you're measuring the negative log of concentration of hydrogen ions. We'll talk more on it later. So let's continue moving. We get to nomenclature. This is sort of what we've already built up a bit. You don't really need to use this for the most part. We'll see most of the acids and bases. We should have seen most of them by now. So we don't really need to use that. Okay, indicators, moving along. What is an indicator? An indicator is a substance that indicates or shows a change in color when you have a change in pH. So depending on what pH you're in, the indicator will show a different color. How do you read an indicator? You'll have a smaller number and a bigger number within a range. So if you have methyl orange, for example, with a pH of 3.1 to 4.4, how do you interpret this indicator? You have an acidic color, a transition color, and a basic color. The lower number shows you the lower limit of the transition range, and the upper number shows you the upper limit of the transition range. So between these two numbers is the transition range, where you'll see an orange color. On either end, you have an acidic color and a basic color. So below 3.1, you'll see red, and above 4.4, you'll see yellow. Okay. Similarly, for bromoethanol blue, litmus, phenolphthalein, you have a range with an acidic side, basic side, and transition. So understand how you read pH. Let's say you have a solution which shows yellow in methyl orange, shows green in bromoethanol blue, shows purple in litmus, and it shows colorless in phenolphthalein. Determine the range of this indicator. Determine the range of pH that you can narrow down this solution's pH to. Type in the chat once you have it. What's the range of pH of this solution if it shows these colors and these different indicators? What's the pH of solution? We've got 4.4 to 8.3. Can we narrow it down more? 6 to 7.6, 6 to 8. Can we narrow it down more? 7 to 7.5. That's getting closer. Okay, let's go through it. So if it's showing yellow in methyl orange, this means that the pH has to be greater than 4.4. That's the first thing we can narrow down. If it's showing green in bromoethanol blue, it's telling us the pH is between 6 to 7.6, which narrows down our range. If it's showing purple in litmus, it means it's between 5.5 to 8. This doesn't narrow down our range at all. And phenolphthalein, if it's showing less than 8.3, if it's colorless, it's showing less than 8.3. So the narrowest range that we can get to, the highest lower number is 6, and the lowest upper number is 7.6, which tells us the range is 6 to 7.6. We can't narrow it down any more than that. What if instead let's say that we changed this green color and it shows instead a blue color. Now what's the narrowest range? What's the range of its 7.6 to 8.3? We can make it a bit narrower. Have a look at litmus. Does litmus narrow down our range? 7.6 to 8. Good. Okay. Does that make sense for everyone? So when you're determining the narrowest range from an indicator, you oftentimes will get a question with different indicators showing different colors. You can narrow down the ranges from looking at the limits on either end and what colors you have. Now, with these 4 indicators, you actually do need to memorize these 4. If it was me, the way that I went about it in my HSC was I would have these 4 indicators because they cover the acidic, neutral, and basic cases for titrations at equivalence. You need to know the name, the range, the colors at each part of their indicator. So at the acidic range, the transition range, the basic range. And if you have these 4, you'll have no problems in using any indicator. So you do need to memorize these. They can rip them at will. Okay. As an extension on that, we need to understand what an indicator actually is. So an indicator actually is a weak acid and a conjugate base. And this understanding not many people really get. An indicator is essentially an acid and base buffer system where one side shows a color and the other side shows another. So for the indicator HA, generally speaking, typically it'll show a redder color. And for a basic color, the A- will show a bluer color. When you have an acidic pH, or when you have an acidic solution rather, This means that you have a lot of H plus. So look what a H plus concentration being high does to our equilibrium system. If we have a really high H plus concentration in solution, this system is going to shift right or left. It's going to shift way to the left. If we have a really acidic solution, it's going to shift all the way to the left, consuming our A minus, trying to reduce some of the H plus, and it's going to make more HA. So we're essentially getting rid of our blue A minus, making more red HA. And that's why you'll see a red color in an indicator. The other case is if you have a basic pH. This would be the opposite, where you're essentially in this system adding in OH minus to the system. If it's a really basic pH, you would be consuming your H plus because these would react together. We'll learn this later. In neutralization to make H2O, cutting out your H plus, shifting the system to the right to compensate that change. And that's why you no longer see red, you instead see blue. Indicators, to summarize, indicators are a weak acid-base pair, similar to a buffer system, which show different colors in acidic versus basic range. And that's why the transition range, which lies between, oftentimes shows a mix of the two colors. So if it's red on one end and blue on the other, and you're at a neutral pH, it's where you have a mix of acid and base. You're at equilibrium at some point where you see a bit of red, a bit of blue, and that's why you have the purple in between. Okay, the red cabbage prac, you would have done this hopefully at school. You boil some cabbage, get out some anthocyanin. The important things to remember about this prac, anthocyanin shows different pHs and it actually has two transition ranges. It will show red on one end, blue in the middle, and yellow on the other end. This is because anthocyanin is diprotic, meaning it has two protons. It is H2 antho. So it has three different colors it can show. H2 antho is red, H antho minus is blue, and that's the first, I guess, transition you'll see, going from pH 1 to pH 7. But if you go from H antho minus to antho 2 minus, that instead shows yellow. And this, now using our understanding of indicators, makes more sense why this indicator in particular has three different unique colors. The other important thing to remember this prac is that anthocyanin degrades or denatures at 120 degrees Celsius. This was in the HSC, so just remember that it will degrade at that temperature and you can't boil too hot or it will break down the indicator. Okay. Any questions? Please type in the chat. Otherwise, I'll continue on. Assume we have perfect understanding. So acid-base reactions, we have three of them. We need to know what happens when you react an acid and a base, acid and carbonate, and acid and metal. So acid and base is neutralization. It makes salt and water. Acid and carbonate makes salt, water, carbon dioxide. Acid and metal makes salt and hydrogen gas. You can be asked to write any of these equations at any point. These should be bread and butter going forward. Okay, applications of acid and base. You have everyday applications and you have industrial applications. You need to know both. So you need to know at least one everyday and one industrial application for an acid and a base. For in everyday applications, for the most part, they're mostly acid. And in exams, I've seen about 95% of exams ask about acid applications. So if you want it to be really safe and you're gunning for like a higher range band 6 or anything like that, try to dig out a base application as well. But for the most part, just an acid one is fine. You can use either, to be honest. 95% are base. Sorry, I meant 95% are base. So for the base applications every day, an acid usually consists of a hydroxide, and acid reflux is a condition where your stomach has too much acid and your valve that keeps your esophagus closed essentially loosens up and can't prevent the backflow of acid up into your throat. So acid comes up in your throat. It's a very painful experience. How do you treat that? You can use antacid. Antacid is a basic tablet or something basic which you can eat, which neutralizes some of your stomach pH, decreasing the acidity and making the reflux symptoms less. When you memorize one of these case studies, take the significance, take the chemistry behind it, so what reaction is actually happening, and have an equation ready to go. You'd want to have, for example, magnesium hydroxide reacting with HCl, which is your stomach acid, making a salt and water. The other two cases, you can talk about preventing tooth decay. So toothpaste tends to have base in it to neutralize some of the acids on your teeth. And baking soda is a more interesting case where your acids react with the acids in dough when you're baking, react with baking soda to perform a carbonate neutralization, a reaction of acid and carbonate, which releases CO2. And that is what's causing your cake to rise as you put it in the oven. If you don't use baking soda, your cake will be rather flat. All those little pockets of air within your cake are actually CO2 bubbles when you use bicarb soda, because it's a neutralization of that carbonate. And that would be your equation you can use. Okay. Industrially, there's two applications that people usually remember. The acid-base spills. So whenever you spill an acid or base, you need to know how to clean it up. The easiest solution here is you say that you use sodium bicarbonate or something that is similar to it. Why is sodium hydrogen carbonate or sodium bicarbonate so good for cleaning acid and base spills? Sodium bicarbonate, amphiprotic, perfect. So it doesn't matter what kind of spill you're cleaning. Whether it's acid or base, if you don't know, sodium bicarbonate will work because it is an amphiprotic substance. What does amphiprotic mean for those who answered? Can donate or accept protons. Good. Roncellary acid or base. Perfect. Second application, we can treat wastewater. So if you have wastewater that contains hydroxide or you have wastewater that contains acid, you can neutralize it by using the converse. So if you have a base spill, you can clean it with acid. If you have an acid spill, you can clean it with base. And there's another example. Okay. So you're basically just preparing for a question like this, where they ask you about how acids and bases are used in one everyday and one industrial situation. You just rattle off one of these with an equation, and you should get full marks. Neutralization enthalpy. So when you neutralize an acid and base, is this endo or exothermic? Exo, definitely. Exothermic. So the prac that you do is you combine two solutions of acid and base typically, and you'll be making a salt and water and releasing energy. So to calculate the delta H, you need to use two important equations. What are those equations? What are the equations? Two important equations. Good. Q equals M cap, and obviously the A, I'd imagine, is your triangle. And delta H is negative Q on N. So we need those two particular equations as follows. Q equals MC delta T. What is M in Q equals M cap? The most commonly confused variable. How do you define M? Mass of water, but even more generally, what if
mass of what's being heated?
Very good. Whatever you're heating is M. So you want the mass of what's being heated. That is your M in Q equals M cap. Do not mix it up with the fuel you're burning. The most common calculation mistake here. Q is your heat. C, what's C? And how do you define it?
Specific heat capacity of water.
And what does that mean? What does it actually tell us? If I say I have a specific heat capacity of 4.18, what does that actually mean? 4.18 4.18 kilojoules per kilogram per Kelvin. Very good, Zoe. How much energy to raise a kilogram of water by 1 Kelvin? This is perfect. So have that clear in your mind. If you have a really high heat capacity, what does that mean? Is it easy or hard to heat something up? If you have a high heat capacity, is it easy or hard to heat something? very hard. And delta T is your change in temperature. So if you heat from 20 to 40 degrees, your delta T is 20. Good. Delta H equals negative Q on N. What do we define N as? The second most commonly confused variable. What is N?
Isn't it just moles?
But moles of what? Moles of what? Okay. So we've got a big mix here. We've got moles, obviously is what it is. We've got moles of water, moles of alcohol, moles of water produced, moles or fuel of what's being used, moles of what's being burnt, and a lot of different answers here. Let's clear it up. N is the moles of what's being reacted. Or in other words, your fuel. In this prac, we're not burning anything, just to be clear. There's a very similar prac in Module 7 where you do enthalpy of combustion. This is not that prac. This is enthalpy of neutralization, a completely separate practical. But they use the same equations to find delta H and navigate heat. So have that clear that generally speaking, you need to understand what N versus M is. M in the first equation is talking about what's being heated, and oftentimes that's your water because you're heating up a solution of water. N is not talking about water at all. We need to have that clear. N is talking about what is being reacted. How much stuff did we react to make this heat is basically what you should be asking yourself. The moles of what's being reacted. In this case, it is your acid and base. It's your reactants, the moles of those. Or in the case of the enthalpy of combustion prac, just to say, to be clear, it's your moles of hydrocarbon or alcohol. It's whatever you're reacting. Have that super clear. Very commonly confused variables here. Then delta H is your heat per mole, and Q is your heat once again. So when you're navigating these two equations, those are the two most commonly mistaken variables. See, yep. So if you're talking about delta, if you're talking about N in terms of your reactants, oftentimes it'll ask about one of the reactants. So they'll say per mole of acid reacted, how much heat would be released? That's the delta H of neutralization. And oftentimes they ask about it in terms of moles of water being produced. So that might be what some of you are talking about with moles of water, but have it very clear that usually it's what the reactant is. Just a point on matching units. Whenever you do any calculation in chemistry, if you aren't sure on units, you will have factors of thousands out oftentimes. It should be clear when you make this mistake, but if you don't know what you're doing and you don't match your units, you will make big mistakes. So whenever you're doing a question like this, your constants guide your units. Your constant for C in the formula sheet is 4.18 times 10 to the power of 3 joules per kilogram per Kelvin. So this tells you that everything else you do in your calculations should be in terms of the units you use in your constant. All your Q values should be in joules, or your masses should be in kilograms, or your temperatures should be in Kelvin. If you don't match your units, you'll be out by factors of 1,000, and it'll be very easy to see. For example, if you do a massive neutralization of many, many moles of reactant, and you only get 5 joules of energy out, you know something's wrong. So use your common sense to mitigate these errors, and you should be okay. Or the other case, if you react a very small amount and you get like 550,000 kilojoules produced, you want to check your units. Okay. So oftentimes, if the question doesn't ask, it won't matter. But if the question does ask, you should always convert to whatever it asks. And usually it'll be in kilojoules per mole. And just with this constant, you can always change 4.18 times 10 to the 3 to 4.18 kilojoules per kilogram per Kelvin. That's the exact same thing. But just make sure you know what units you have when you do this. A lot of people will blindly use 4.18, and sometimes it fixes itself, sometimes it doesn't. That's where you have silly mistakes, but it's not really a silly mistake. You just haven't done it correctly. Make sure you match your units. Very important. Okay, so the typical questions you'll get are where you're combining a volume of one concentration acid and a volume of another concentration of base. You have a temperature change of some sort, and you need to find, for example, the delta H, or you need to find how many moles of, you need to find delta H. It's a very common question type. So what's the most common mistake people make within their first line of working? Can anyone identify it for a question like this? What's the most common mistake that people make in a question like this? Before you even do any unbalanced equation, sure, that's the first one. There's a second thing as well. Right after you balance your equation, what's the next most common mistake? Not converting units. It could be, but there's one even more pressing problem. If you don't convert mils, you'd still fix it in the end. It is to do with the volumes though. Yeah, so forgetting to add the volumes together would be a big problem. Actually, in a question like this, wouldn't actually affect it too bad because you're doing a limiting reagent. But in a questions where you do later on with pH, that's actually the most pressing issue. So actually for this question, it's not too worrisome because as long as you find the correct moles doing your limiting reagent, it's fine. But in the later questions where you need to find pH after you do a neutralization, you must remember to combine your volumes together. Okay. Moving on to the acid-base theories. So we have Arrhenius and Bronsted-Lowry as the syllabus prescribed. What you need for each theory is a definition, how it improved on the one that came before it, and the limitations of that theory. So just going through them all quickly, Lavoisier said that acids would contain oxygen. This worked for things like HNO3 and H2SO4, but did not work for many other acids that didn't contain hydrogen. And it also didn't work for things that contain oxygen and weren't acidic. Davy came along and said all hydrogen-containing compounds are acids. This was false because acids that, while some acids would be classified as acids on this definition, things that didn't contain hydrogen could still be acidic, like CO2, and it didn't explain why some substances that had hydrogen weren't acidic, like methane. Which introduces our big hitters. So Arrhenius says that acids are substances which in solution ionize to make H+. HA dissociates into H+ and A-, and bases ionize in solution to make OH. BOH goes to B+ and OH-. Neutralization was defined as the reaction of H+ with OH- to make H2O. It improves on Davy because it talks about the ionizing property of acids, which for the first time explains conductivity of acids and also lays the groundwork for why pH works, and also explains neutralization. But there are many limitations. So the main ones are that it doesn't acknowledge the role of the solvent, and you cannot explain acidic properties outside of solution. Everything in Arrhenius has to happen in solution. So that doesn't explain gaseous acid and base, as we say here. And that's probably the main one. The other ones are also important, but we've got to keep moving. Bronsted-Lowry's theory develops further on this, and he says that a substance which tends to donate protons is an acid. This now captures things that happen outside of solution, and it acknowledges the role of the solvent in solution. That is a really important thing to understand because that's the whole of inquiry question 2, the role of the solvent. So let's talk a bit more about that. Bronsted-Lowry expands on definitions saying that when an acid goes into solution, it doesn't just necessarily just dissolve and turn into H+ and CH3CO- in the case of acidic acid. The role of the solvent is that H2O will react with the acid to make hydronium, which is exclusive to Bronsted-Lowry. The role of the solvent is that it contributes to the acidic property in solution. And hydronium is only in Bronsted-Lowry. If you get asked a question where you're asked to determine which equation shows Arrhenius or which equation shows Bronsted-Lowry, You're looking for the one that has hydronium in it and has water in it. That is the telltale that you're looking at a Bronsted-Lowry equation. Bronsted-Lowry bases, on the other end, are substances which accept protons. And something like ammonia can now be explained as a base because of its interaction with the solvent, once again. So when you see water in the equation, it's a Bronsted-Lowry equation. NH3 reacts with H2O to form NH4 plus and OH minus. This is your Bronsted-Lowry base in action, accepting a proton from water. Then Bronsted-Lowry neutralization, it is simply defined as an acid-base reaction, which is an exothermic proton transfer. So you're transferring a proton from an acid to a base. And that is now our working definition for neutralization. And it introduces the idea of conjugates. Spotting conjugates is really easy. You just look at the two substances that look very similar and are different by a single hydrogen. That is your conjugate pair. So if you're looking at this particular equation, HCl is our acid. The conjugate pair of HCl is going to be Cl minus. That's our conjugate base. And for H2O and H3O plus, H3O plus is always going to be an acid. So this is our conjugate acid. And H2O is our base, therefore. So water can be a base. Water can also be an acid. And that introduces the idea of our amphiprotic substances as we go on a bit further. So water is neutral, as we all know, it's around pH 7, but Bronsted-Lowry says water is not necessarily a neutral substance. In fact, it can be an acid or a base. Bronsted-Lowry was solely responsible for explaining that water is more than just a solvent. It actually contributes in these reactions to make acid and base properties, and we'll talk more on that. The big advantages of Bronsted-Lowry are listed here. So explains non-hydroxide bases, explains amphiprotism among these advantages. And then in terms of the limitations, he says that he's still not able to explain things like acidic oxides or basic oxides because these don't have a proton transfer. And therefore you can't explain those reactions between substances which are acidic or basic oxides. So to summarize, Arrhenius and Bronsted-Lowry, the big difference is Arrhenius said that acids ionize to make H+, and they don't, and Bronsted-Lowry said they donate protons to form H2+. Bases are ionizing to make OH-, and protons are accepted instead. Lewis expands on this a little bit, but for the most part, you won't be asked on Lewis explicitly. And this is, I guess, an older style question becoming much more uncommon. You're going to be tested on application-based things moving forward, less recollection and rote learning. Table for you to memorize to help you understand. Inquiry question 2, using Bronsted-Lowry theory. And this is what I was mentioning about how the whole inquiry question is about the role of water in solutions and bases. We first talk about conjugates, proticity, and strength. So there are two cases, sodium hydrogen carbonate and potassium dihydrogen phosphate. These are two substances which are amphiprotic. How do you show a substance is amphiprotic? What do you do? Question asks you 2 marks. Show that sodium hydrogen carbonate is amphiprotic. What do you do? How do you show it in an equation with acid and base? Good. Okay. So I like C's answer best. React with H3O plus and react with OH minus. The reason why I don't like reacting with H plus as much is because H plus is by Arrhenius's theory. And we're now in Bronsted-Lowry. When we talk about amphiprotism, we want to use everything Bronsted-Lowry. So H3O plus and OH minus is the best. Do not show it reacting with water because water is amphiprotic too. That's not a proof of amphiprotism as strongly as doing with H2O plus and OH minus. Okay. Acid and base pairs, as we said before, it's a difference of 1 hydrogen is how you determine. Proticity. What's proticity? Proticity is how many protons an acid can donate. You can have monoprotic, diprotic, or triprotic acids, meaning 1 proton, 2 proton, 3 proton. Triprotic acids have 3 protons, and as I said before, the really important one to remember is citric acid. You just cannot figure that out in the exam. The same way as if you hadn't seen CH3COOH before, you wouldn't know, but now you do. When you ionize acids, it becomes harder and harder to ionize. The ionization energy will increase from the first to the second to the third ionization, and this is because you'll have relatively less electrons with more protons in the center, so it's going to be held on tighter. And you can see that reflected in these Ka values. So Ka, let's introduce that. What is Ka? What does it tell us? Acid strength, good. And a big Ka versus small Ka. What's the difference? Big Ka tells us what? Small Ka tells us what? Feel free to unmute. How readily it dissociates, correct, but say you have a massive Ka, or like a big one like this, 1 times 10 to the 3. What does that tell us about acid strength? Is it a higher in strength or lower in strength? Good. So LR, big Ka equals strong acid, that's all we want. And we consider, generally speaking, a Ka bigger than 1 or a lot bigger than 1 is going to be strong. Below 1 is where you consider an acid to be weak. So what does strong versus weak acid mean? How do we separate those? Strong versus weak acid. Ionization percentage, rarely dissociates into the ion, but where do we cut off? Where do we say an acid becomes strong or an acid becomes weak? Like what percentage? Yeah, we pretty much say if an acid dissociates pretty much 100%, you consider it strong. Complete dissociation is strong. And anything less than 100% we consider weak. So even if it's like 90% or 80%, we consider that acid to be weak. Which makes sense. Obviously, you can't have 100% ionization in reality, but if you have a very, very close value to 100%, like 99.9, you're pretty much considered to be strong. Let's talk more in Ka later. So 2 common misconceptions, let's get out of the way. The number of hydrogens does not always correspond to the proticity. So you have 4 hydrogens in ethanoic acid, but we know this is monoprotic. And for those of you who have been through Mod 7, which you should have been, we should know that's because we have a carboxyl group. And a carboxyl group, each one can lose 1 hydrogen. These C to H bonds are really stable, so they will not break. You cannot ionize those bonds. In citric acid, this is what it looks like. We have 3 carboxyls, and each one can lose a hydrogen each. We cannot lose the hydrogen from OH, that is a stable bond there, but each of these can go, and that's why citric acid is triprotic. Second common misconception, higher proticity does not always mean higher final concentration of H2O+, and that's because of the property of strength. If you have a very weak triprotic acid, it may not have a higher concentration than a strong monoprotic. So we'll talk more on strength as we go. Amphiproticity, we introduced this idea just before. Amphiprotic substance can act as both an acid and a base depending on the situation, can both donate and accept a proton, and it has 2. You can always prove amphiproticity through 2 equations where you either react with H3O+ or OH-. So take this as your example that you copy into whenever you need to do a proof. Acid strength. So moving on to acid strength, as we mentioned before, a strong acid is one that will completely dissociate 100%, and you oftentimes indicate with that with a single arrow going one way. Comparing that to a weak acid, it will often form an equilibrium and is a reversible reaction, as we learned about in Module 5. And we show that with a reversible arrow instead. There are 5 strong acids that come up over and over again in HSC. There's 2 others that you may know as well, but these 5 strong acids you must know. The 5 strong acids are HCl, HBr, HI, HNO3, and H2SO4. And the ones that you see are the ones to do with chlorate and perchlorate. So perchloric acid can also be considered strong. But if you know these 5 strong acids, you then know all the other weak acids. So memorize it that way. If you know these 5, every acid that is not one of these 5 or one of the perchloric acids, it is then weak. So HF, acetic acid, every other acid is then weak. Another common misconception, weak acids and bases are able to neutralize less compared to strong acids. This is probably the most common misconception. The truth is, it doesn't matter how much or how strong an acid or base is in relation to how much it can neutralize. If you have 0.1 molar of HCl, that will be able to neutralize the exact same as 0.1 molar of CH3COOH. It doesn't matter that CH3COOH is weak. These will both be able to neutralize the same amount of OH minus. It doesn't matter that they're weak. And then beyond that, if you have 0.1 molar of H3PO4, this would be able to neutralize 3 times more. So what does that tell us about what determines how much base an acid can neutralize? We have 0.1 molar here. It tells us that proticity determines how much base an acid can neutralize, not its strength. Are there any questions on that concept? Very commonly mixed up. I can explain it again and in more detail. So just to explain that, in a strong acid, it will dissociate 100%. You'll have 100% of your ions turning into H plus and H2O plus. Very intuitive. For a weak acid, you might only have, say, 10% dissociation. So only 10% might dissociate into H plus. But what happens as you start to neutralize this H plus? You add OH minus into solution. As you start to neutralize, you will destroy all of the H plus that is free. What's going to happen from this point? Are you finished with your neutralization, or can you keep going? You add in OH minus, reacts to H plus. What happens from here? Will anything happen to the equilibrium? Not too sure. All right. So if we neutralize off our H plus with OH minus, decrease in H plus concentration, so we shift right. Good. That's better. So the system would then shift right to replace some of that H plus and dissociate 10% again. If you still have more OH minus, that's going to be reacted off and it's going to shift right again. And then you're going to have this continual movement of acid into dissociation, and you'll be able to neutralize off as much as the amount of H you have present, regardless of whether it's weak or strong. Hopefully that makes sense. But important to note that the proticity of an acid determines how much base it can dissociate, how much it can neutralize. Yep, absolutely, I can go again. So just to explain it one more time. If you have a system of a weak acid, HA dissociates into H plus and A minus. When you're neutralizing base, it's not as simple as an acid, which is strong, which just dissociates 100% into H plus, which is ready to be knocked off by OH minus. In a weak acid, you might only dissociate 10% of your H plus initially. And if you add in OH minus, that's going to react with the H plus to make water. So that would basically react with all of your H plus if you add enough OH minus initially. And if you decrease your H plus concentration, the equilibrium system is going to shift to counteract the change in accordance with LCP, which is going to make it go to the right, producing more H plus, and producing more A minus. Does that make sense, first of all, Sumya? Because you're going to be reacting off OH minus, the system is going to be able to make back some of that H plus in free ion form. And if you still have more OH minus present, the additional OH minus is going to be able to react off the further H plus, system will shift again, and eventually you'll completely shift all the way across after you've done this enough times to get rid of all the HA, which is why the total number of hydrogen is more important than the strength. In fact, it's the only thing that's important when determining how much base we can neutralize. Okay. Strength of conjugate acid-base pairs. Super poorly taught concept at school. So when you have a conjugate acid and base, you're always able to figure out the strength of the conjugates based on the other one. All you need to remember is if you have a strong acid, the conjugate base is going to be a very weak base. If you have a weak acid, the conjugate is going to be a weak base. And if you have a strong base, the conjugate is going to be a very weak acid. A weak acid versus a very weak acid is they're both weak, but when we consider conjugate base pairs, it's important because a weak acid is still stronger than a very weak acid. Okay. So if we look at an equation such as this one, HNO3 reacts with NH3 to make NH4 plus and NO3 minus. The typical question they'll ask is what's the strength or what's the acidity of the solution you produce? Or what's the basicity? Is it acidic, basic, or neutral? So we can figure that out by looking at the conjugates. HNO3 is a strong acid. NH3 is a weak base. We know this from our knowledge of strength. Therefore, the conjugate of HNO3 is NO3 minus, a very weak base based on our conjugate system. And the conjugate of a weak base is a weak acid. Therefore, if we're asked what the acidity, basicity, or neutrality of our products are, because we have a weak acid and a very weak base, the weak acid would be contributing to more of, like, it would make more H plus compared to OH minus that the NO3 would be making. And so this is an acidic solution, therefore. Okay. Strength versus concentration. Strength is how much an acid ionizes. So if we're looking at strong versus weak, we'd simply be looking at a situation where we have little dissolution compared to one we have complete dissolution. And dilute versus concentrated is how much undissociated acid molecule you start with versus how many, yes, you'd be looking at how many undissociated acid molecules you have. If you have lots in combination with all the H plus and A minus you make, that would be concentrated. If you have very little, that would be your dilute case. So these are dilute solutions as opposed to concentrated. Sumya says, if it was strong acid and base, would it be neutral? Correct. And the reason would be because the conjugates would be very weak acid and very weak base, meaning that you pretty much are going to have a neutral solution. Because very weak acid, very weak base, we basically consider that to be neutral. So you have two neutral substances being made, virtually neutral, and you'd have a neutral solution. And this is important because it explains your pHs at equivalence in your titrations. So we'll use this explanation again in a second. So you need to be able to make a model of strength versus concentration in your exam. Something like this was perfect. Just be careful when you're making a model. Try not to use color because color is grayed out in your HSC. It's scanned up in grayscale. So make it something that's distinct without using color. pH probe. You have this instrument which is able to measure pH. Not super high yield, but it's just in there because the syllabus says so. The pH probe needs to be calibrated before you use it. You need to clean it between uses so there's no contamination, and it gives you an accurate reading of pH based on how much hydrogen there is. Okay. Some household substances and their pHs. Soft drink, red wine, orange juice, and aspirin are the 4 syllabus listed ones. Like there's a medicine that's listed. So These are all acids, soft drink having citric acid, red wine having tartaric, malic, and citric. Orange juice has citric acid, and aspirin is acetyl salicylic acid. So they're all acids that have a pH of less than 7. Oven cleaner is an example of a base. I just threw it in as well, so you have an example if you need. And that is either sodium hydroxide or potassium hydroxide. Okay. Now we're starting to get on the quantitative part of Mod 6. Are there any questions? Or are we okay? Okay, let's keep going. Using pH to find strength, in order to calculate pH, you need to know the equation. So pH is negative log of hydronium, and you can rearrange that as H3O plus concentration is 10 to the negative pH. So we should be able to calculate a pH. Say we have a hydrogen concentration of 0.1 and a hydrogen concentration of 0.01 molar. What are the pHs of these two solutions? Type it in chat. First person who gets it correct gets a thumbs up. What are the pHs of 0.1 molar and 0.01 molar? One's correct for the top one. Isabel's got both first, so Isabel gets a thumbs up. 1 and 2. And if we did 0.001, we would get 3. So 1, 2, 3. What is the relationship between pH and hydronium from the log scale? Factor of 10. So if we increase pH by 1, go from pH 1 to 2, this means we have a decrease in hydrogen concentration or hydronium concentration by 10 times. That relationship you need to have clear in your head. They love to ask that question. And going the other way, if you decrease pH from 2 to 1, you are increasing your hydronium concentration by 10 times going the other way. And that makes sense because a lower pH represents more acidic conditions. That's why pH will go lower as you become more acidic. POH is the exact same type of calculation where POH is equal to negative log 10 of hydroxide concentration, operates on the exact same scale, factors of 10, that's from the log 10, and it is the opposite of pH in the sense that it measures hydroxide. We'll relate these together in a second, why it makes sense they're opposites. But the only thing that you should really take away as well is you can rearrange these equations like this, where the concentration is equal to 10 to the negative pH. So you need to be able to convert from log to indices comfortably. Sig figs. How many sig figs do we leave pHs to? Say your question gives you 3SF as the smallest. How many sig figs do you leave your pH to if your answer is a pH at the end? Couldn't trick anyone. So 3dP. pHs and anything with a P, so pH, pKa, you leave it to decimal places for pH. So if the question gives you 3 sig figs, your answer for pH is the 3 decimal places. Relating pH and POH. So at the moment, our ideas of pH and POH are separate. Let's combine them together. The first thing we need to understand is that water is a substance that will react with itself to make hydronium and hydroxide. It is an amphiprotic substance. In doing this, one of the waters is acting as an acid and one of the waters is acting as a base in the same equation. This happens to a very small extent where water reacts with itself and makes hydronium and hydroxide. It's a very, very low amount of H2O plus and OH minus being made. So we can make an equilibrium expression. As we know, KEQ is equal to concentration of products over concentration of reactants. And the KEQ expression is going to be H3O plus for this reaction times by OH minus. So why did I leave out water? Why can I leave out water from this KEQ, or why should I? liquid, and we want to leave out our liquids, we want to leave out our solids because they are pure. So it's just H2O plus times OH minus, and this is in fact what we call Kw, our auto-ionization constant of water. And this value is equal to 1 times 10 to the negative 14 at 25 degrees Celsius. Okay, so why does this matter to us? It's all about to make sense. I introduce this value because if we take that relationship where H2O plus times OH minus is equal to 10 to the negative 14, and we log both sides, we end up getting the log of H2O plus the log of OH minus, when you separate out these two logs, equals to negative 14. Negative log, if you apply negative to all the numbers, times by negative 1, negative log hydronium minus negative log or minus log of hydroxide is equal to 14. This delivers us the relationship that pH plus POH is equal to 14. And through the auto-ionization constant of water, we're able to derive the relationship between hydrogen concentration and hydroxide concentration at 25 degrees Celsius specifically. Why does it have to be 25 degrees Celsius specifically? Why am I so pedantic about that? Because temperature change will affect KEQ and KW. Good. The only thing that can affect K. So then all of a sudden, we have this relationship between hydroxide and hydronium. As one rises, the other falls. As one falls, the other rises. And it's this relationship where you're at pH 1. This not only describes hydronium, this also describes hydroxide at the same time. Because of that relationship where they're equal to 10 to the negative 14 if we're talking about water. And that sliding scale works the other way. If you have a hydronium concentration of 10 to the negative 1, your POH would be equal to 1. And that's related to a hydronium concentration of 10 to the negative 13, or pH of 13. So they measure acidity and basicity based on hydronium and hydroxide concentrations. They're related together directly. Okay. In acidic and basic solutions, this is basically just what I'm explaining. In a neutral solution, that is also why pH 7 is considered neutral, because that is when your hydronium concentration equals to your hydroxide concentration, or 10 to the negative 7. An acidic solution will have more hydronium compared to hydroxide, reflecting a pH which is less than 7, and a POH which is greater than 7. And finally, for a basic solution, a pH which is greater than 7, and a POH which is less than 7. Okay, so starting to build up the ideas, linking everything together. Now, if I have a low pH, is my acid strong? Answer yes, no. If I have a low pH, is my acid strong? If I have a low pH, is my acid strong? Say my pH is 1. Is my acid necessarily strong? It would be likely, but not necessarily. pH of 1 is really low, so like probably it is. But there are more factors that affect pH than just strength alone. If I have a pH of 5, probably a better example, can I say that the acid in solution is a weak acid necessarily? And the answer again is no, because what if you just had a really dilute strong acid? That could give you a pH of 5. So understanding now that pH is not an accurate measure of strength. I want everyone to spell that idea. It is not the best measure because you have multiple factors that affect pH, not just strength. And there's 3. We need to consider that, first of all, yes, as we know, strength would affect pH. So if a acid is really, really strong, it'll dissociate 100% and you'll have a higher concentration of H plus. So if you have H plus being 1 mole per liter, this would deliver us a pH of actually 0. This is possible. You can have pH of 0. And if you have an acetic acid solution, which is of same concentration, but is much weaker, you might only have 2% dissociation and get 0.02 mole per liter, something which would have a greater pH, something of 1 point something. So that's the first thing. Acids that are stronger will tend to have a lower, will have a lower pH of a equimolar weak acid. First understanding. Secondly, solutions that are more protic and have the same degree of ionization will also have a lower pH because they can ionize more. So for HCl, once again, it'll be a pH of 0 if you have hydrogen concentration of 1. What's the pH of this H2SO4 if it dissociates 1.2 mole per liter? For our purposes in HSC, we can consider the second ionization of H2SO4 to be strong. So let's just say it's 2 mole per liter of H plus. What's the pH? Type in chat. What is the pH of H2SO4 that delivers a H plus concentration of 2 mole per liter? Should be just a quick calculation. pH equals negative log of hydronium. Everyone's probably staring at the negative number and doubting themselves. But it is in fact a negative number. pH can go negative if you have a strong enough, if you have a high enough concentration of hydronium. This is actually a negative 0.3 pH, and I've left it to 1 sig. Based on the question stem, if I've given you just 2 mole per liter, it'd be 1 dP. So the point here is an acid that is equimolar and of similar strength will have a lower pH because it can ionize an extra proton compared to something that is less protic. And the final and probably most important factor to consider that is going to affect us is concentration. So acids of different concentration will have different pH, obviously, because the more acid you have, the more hydrogen you're able to dissociate, and the less acid you have, the less hydrogen you're able to dissociate. Hopefully that's quite intuitive. If you have 0.001 mole per liter of HCl, a much lower concentration, even though it's a strong acid, it will have a higher pH compared to acetic acid, which only partially dissociates and has a much higher concentration, will deliver a lower pH in that instance. So be clear that for the factors that affect pH, it is not just strength. You cannot say an acid that is of pH 1 or pH 2 is always strong. Most of the time it will be. It will tend to be, but we can't know for sure. So just keep that in mind and consider that concentration will also affect pH. 3 main factors: acid strength, acid concentration, acid proticity. The strength and concentration arguments are true for bases as well, but you don't really talk about proticity of a base. Okay. So we'll get onto the conductivity stuff in a second. Let's keep going. Neutralization pH. So this is the next calculation we introduce, where you neutralize 2 solutions of acid and base. You have a acid and base react to make salt and water. How you approach these questions is going to be a limiting reagent. So it's a limiting reagent followed by a pH calculation using the excess reagent. So it's a 2-phase question, these ones. Example question is, you have pH after 30 mils, asked to calculate pH after 30 mils of 0.10 mole per liter sodium hydroxide is added to 50 mils of 0.30 mole per liter hydrochloric acid solution. And you need to include a balanced equation in your answer. So the balanced equation is as such: acid and base make salt and water. you first need to execute a limiting reagent calculation. So back to module 2, we have sodium hydroxide reacting with HCl, and that will form your salt and water. Which of these is limiting? NaOH or HCl? Look at it carefully. What's limiting? NaOH. NaOH is limiting because there is not enough NaOH to react all the HCl. And so based on that, we can find out what our excess reagent is. All of the HCl will get reacted and there'll be a little bit of NaOH left over. That's what you need to calculate your pH based on. So the excess other way around. All your NaOH will be reacted and you have a bit of excess HCl left over. Based on that, you find out how much excess HCl there is, 0.012 mole. And this is that step I was talking about before, the really important one in a neutralization question, where if you're combining two volumes of solution, you need to consider that your final concentration of hydrogen will change based on that. So you have your moles of HCl, you need to calculate a new concentration of HCl because of the new volume. C equals N on V. And so you put moles over volume and you can find that the final answer for HCl's concentration is 0.15. As this is a strong acid, it would dissociate 100% into 0.15 mole per liter H+, and putting that into our pH calculation, we can turn that into 0.82 to 2 decimal places because the question gives us 2 sig figs in the stem. Does that make sense for everyone? Neutralization, calculating pH. Okay, I put buffers here, even though it's at the end, because you need buffers in order to explain titration fully. So what is a buffer? What are the components that make up a buffer? And how do you define it? I'll give everyone 30 seconds to type in chat. Definition of a buffer. How do you define it? Okay, so we've got some half-mark responses and some full-mark responses. The full-mark responses mention both things important to a buffer, that it's a weak acid and its conjugate base, or vice versa, and it's able to resist change in pH is the second thing. So whenever you define a buffer, you need to mention both. I'll give a thumbs up to the first one in. So when you talk about a buffer, it's a weak acid and conjugate base, acts via an equilibrium system to resist changes in pH. Let's talk about how exactly that works. So for a buffer mechanism, you have an equation HA plus H2O goes to H3O plus and A minus, and also the conjugate can act with water as well. So usually when you write out a buffer, and these should all be aqueous, if you were to be, apart from water, AQ, AQ, AQ plus water goes to OH minus AQ plus HA. So the buffer system has two equations. You always want to show two equations for a buffer, one of the acid reacting with water and one of the conjugate base reacting with water. And if it's for a base and a conjugate acid, you can show the same thing. So how does an acid resist changes to pH? Well, how does a buffer resist changes of pH in terms of acid first and then base? When you normally add H3O plus into a solution, your pH will drop. If you just add H3O plus, because your concentration will rise. So say you, in this buffer, say that your buffer is actually CH3COOH, but it could be any weak acid. If you add HCl into this solution, how will it affect the buffer system? Talk about it through the first curve. how will HCl being added affect this buffer system? Talk about it through the first equation first. HCl is added. How does it affect? Good, okay. So equilibrium will shift left due to the increase in H3O plus concentration. This is good. So if you add HCl, if we're going to do it by Bronze Larry, HCl will react with water. And imagine it's reacting with water, it's going to make H3O plus concentration rise. So that's going to cause H3O plus to rise in accordance with Le Chatelier's principle, which states that a system will counteract change to minimize that change. The system is going to shift left to get rid of this newly added H3O plus. That will decrease your H3O plus, consume some of your A minus, and make H2O and HA. So instead of your H2O plus concentration just increasing by the amount of HCl you've added, does everyone see that all that H2O plus you just added is being consumed by the system in this resistance? So what effect on pH does it have? Is pH going to change by a lot? Will pH change by much? It will not, because that initial change that you made is counteracted and offset by this compensation, this counteraction. And so your net change in H2O plus is like tiny, like it's a little bit. It's a little bit. You'll have a slight decrease in pH, but the mass change in H2O plus has been mitigated, resisted, and will not be observed in a pH because it's been turned into HA and H2O, which both don't contribute to pH. HA, even though it is an acid molecule, is not dissociated, so it's not contributing to pH. H2O is basically neutral, so it's not going to contribute to pH either. So this is what's happening on your graph. As you add acid, initially, there's very little change in pH. But at some point, you start to have a massive drop-off. So what's happened here? Why do we start to see a big drop-off as you keep adding acid? Buffer capacity exceeded. Good. And that would mean when we say buffer capacity exceeded, what have we fully reacted? What's causing this buffer to be used up? Good. We've used up all of A. So if we keep adding more hydronium and say this yellow arrow is some new hydronium and we add too much, we add so much that we react all the A minus and we can only mitigate a little bit of the change. And beyond then, any H2O plus we add cannot be reacted with A minus. That is when we've exceeded buffer capacity, which is how much hydronium or hydroxide the system can consume. Once you reach buffer capacity, any further H2O plus you add will simply contribute directly into solution and your pH will plummet because of that. Explaining it through base. So you can use the same equations to explain it through base. Let me rub all of this out. So let's now take the base and let's use the first equation again. We could use the second equation too, but let's take the first equation for some variety. So if you add OH minus into solution, how is that going to affect the first equation once again? So you add OH minus, how is that going to affect the first equation? And how does it resist the change? Good. Okay. So OH minus is going to react with the H3O plus, forming us some H2O, in fact, two of them. And so the addition of OH minus will decrease how much H3O plus we have. System will therefore shift right. I don't know what to refer to by name, smiley face, but shifts across to the right, and it will increase our H3O plus concentration back up whilst consuming some H2O and HA and making more A minus. Yes, the recording will be uploaded after the sessions. It will take maybe a few days to be up, but it will be up. Okay, so the system will shift to the right, and that decrease in H3O plus concentration we initially saw will be mitigated. We're only going to have a small decrease in H3O plus compared to before, where you would have lost the entire amount here and had a massive change in pH. So be comfortable explaining the buffer through these two graphs, and know that buffer capacity is the volume at which all of the conjugate acid or base is consumed. Okay. Titration. So different titrations you can see the acid-base, precipitation, complexation, and back titration. These are mod 8, so don't worry about them for now, but sometimes schools can mix them in earlier to test you anyway. Standard solution, titrant, analyte, titer, aliquot, equivalence point, endpoint, titration error, all important to know. A standard solution is a solution with known concentration. A titrant is a solution of known concentration solution of known concentration that is used to titrate. The analyte is usually your unknown concentration in the conical flask. Titer is the minimum volume of titrant required to reach endpoint, and aliquot is the volume of analyte that you put into the conical flask, typically 25 mils. Equivalence point can be defined as the point of complete reaction of analyte or complete neutralization. This is different to endpoint. Endpoint is the point at which you observe change, whether it's a color change, whether it's a change in conductance. It can be any change you observe to show that you've reached equivalence point. These are not necessarily the same. In a titration that is good, they will be pretty much the same. But you can have a difference between equivalence point when you reach complete neutralization and when you actually see your indicator working. And that difference is what we call titration error, the difference between equivalence point and endpoint. As I'm sure you know, this is what a titration looks like. Be able to draw a diagram of a titration well, use a ruler, draw labels using a ruler and touching the lines of your equipment. Titration method. You need to be able to talk about selection of primary standard. So for a primary standard, it has to be something that is soluble, definite composition, is pure, non-volatile, and has high molecular weight. The reasons for these are all rather self-explanatory, but the most important of which is high purity. You have to avoid what we call hygroscopic substances that draw in water. So that's NaOH, KOH, and H2SO4 should be avoided as primary standards. And substances that are volatile, like high concentration of HCl, can also lose mass after you weigh them. So be very wary of using these substances in particular. If you can't use a substance as a primary standard, but you still want to use it, you can use it as a secondary standard. So a secondary standard is created by titrating that solution to know its concentration for sure. So if you want to use NaOH, for example, you can titrate NaOH to find its exact concentration once the solution's already been made, and that will allow you to then use that NaOH without having to use it as a primary standard. To make a standard solution, there's a few steps. You're going to weigh your primary standard on a scale. This gives you mass, and if you know its composition, you can multiply mass by divide mass by molar mass to get moles. So you know your moles from weighing your primary standard. When you dissolve your primary standard, you'll make a solution, pour it into a volumetric flask, fill it to the gradation line with the bottom of the meniscus at the line, and this gives you a precise volume, usually 25 mils. So now that you have moles and volume, you can apply this and find concentration exactly. So I went through this with the year 11 this morning as well. Concentration equals moles on volume. Okay, and the procedure of doing this, there's a few specific things, but that's the main idea. You should have Also at the end, inverting 20 times to make sure it's homogenized. Selecting an appropriate indicator. This is why I said you need at least the 3 cases: methyl orange, bromothermal blue, phenolphthalein. Litmus isn't as good as bromothermal blue because the range is slightly wider. But you need these indicators for when your salt is either acidic, neutral, or basic in a titration, because your equivalents will be located in those ranges. For a strong acid, weak base, you use methyl orange. For a strong acid, strong base, you use bromothermal blue. And for a weak acid, strong base, you use phenolphthalein, because that will be where your equivalence point is located. Rinsing of glassware, you're going to want to use demineralized water for the volumetric flask and conical flask, because in these specific glasswares, the moles must be kept the same. It doesn't matter what the concentration is once the solution is in, you just need the moles to be accurate. And for the pipette and burette, you rinse these using a solution because they are transferring a specific concentration. The concentration must be known here. And so you cannot dilute these, you must rinse with the solution they contain. Making the solutions for titration, fill the conical flask with an aliquot. So use your pipette bulb filler or whatever other pipette you have. And for the burette, you want to fill it up just above 0 mils. Let out any gas bubbles by flicking the stopcock and letting out a little bit of the volume at the bottom, which will mean that there's no gas bubbles increasing your volume at that lower area. You want to take wherever the volume is, ideally at 0 mils, and then when you finish, you will have an accurate reading as the numbers will increase going down. Performing titration, hopefully you've done it as well. So it's going to be 1 rough titration, which you don't include, and 3 titrations, which should be concordant, is when you have a reliable titration. Making sure that the color change lasts at least 15 seconds and swirling until you can definitely see no more color change beyond that point. And just important to slow to a dropwise amount right before the expected equivalence from your rough titration. Okay, so titration calculation, typically you'll get a table with 4 values. You should know that if you have a bigger first titration value, you're always going to exclude it and discount it as the rough. And to do your calculation, you'll need to make an equation of the neutralization, find out the moles of your primary standard if you're asked to, find your average titer, the amounts reacted, the concentration of your analyte from that, and those steps are pretty standard for any titration calculation. So if you want to have a go at this one, take a screenshot and have a look at the answer later. Making sure that the things you don't forget are an equation, rounding error. So with your rounding error, what I mean is when you're doing your calculations early, keep your numbers exact and even save them in your calculator. So for everyone who doesn't know how to save yet, you can always save numbers. For example, I put 88 in my calculator. I can save this number by pressing Shift Store, and I can pick one of my letters, for example, A. This saves my answer to that letter, and I can recall it by doing alpha A. My A is equal to 88. So you can keep exact numbers in your calculator instead of writing out all the massive numbers. You can reduce it to something like 0.235 ... and then label it as B as an example. Make sure you have the right sig figs and have units as well going along. Okay. Conductometric titration. Conductometric titration is where you're measuring pH based on hydrogen, you're not measuring pH, you're measuring how many free moving charged particles you have in solution. And oftentimes it reflects H plus and OH minus because they are lightweight charge carriers, which move around very readily in solution, carrying charge from one side to the other. To do a conductometric titration, you do the same steps as a normal titration, except you're just going to let your stopcock flow at a constant rate and record a time versus conductance function, where as you release the constant amount of your titrant, you're going to have changes in your conductometric curve at a constant rate. And you'll see as we go on why this reflects exactly what it does. But the idea is if you have more ions in solution, this will lead to high conductivity. And if you have ions which are more lightweight, as opposed to being bulky, bulky being heavier, so anything that is not OH or H plus we consider to be bulky, whereas H plus and OH we consider to be lightweight. If it's more lightweight, it'll be more conductive. So if you have more lightweight ions, they will have more conductivity as opposed to bulky. Okay. So let's get into our explanation of these curves. We've talked about conductivity. You should know how to explain each and every one of these 8 curves. Might seem daunting, but if you truly understand what's happening, you don't really have to memorize anything. You can always figure it out anyway. So let's talk through them one by one. For a strong acid, strong base, you have these 2 pH curves and conductometric curve. To explain a curve, the questions will come as a 4-marker where you're asked essentially, explain the key features within this titration curve. What I would do in an exam is pinpoint exactly where I want to talk about with a number. I know that some schools are finicky and don't like you writing, but I would just number on there anyway and define what that point is in your response. So I'd say at point 1, pH is low, and if you had the concentration of the acid from the titration, you can deduce that it is definitely strong, but oftentimes a low starting pH reflects a strong acid. As you add base, the pH will start to rise at an increasing rate, because you are starting to neutralize that acid with OH minus. And you would show an equation here to show that neutralization. This is increasing at an increasing rate because it's fighting against the log scale. So you need to add 10 times the base concentration, or you need to increase pH from 1 to 2, you would need 10 times more base to neutralize than to go from pH 2 to 3, which is why the curve will increase by 1 for 10 units. And then for the next increase of 1, it only requires 1 unit. And the next increase is only 0.1. And that's why your curve starts to accelerate upwards, because you're fighting against this log scale. And that's due to the log scale. You have a pH at 7. You have this massive acceleration through 7, where you have equivalence point. And this is where you have complete neutralization. Complete neutralization of all the acid, all the base gets neutralized, and you have equal amounts of both. Technically 10 to the negative 7 in this case. Why is the pH neutral? Can someone explain that? Why is the pH neutral in this particular titration? Product is a neutral salt, correct? Because you're going to make a very weak acid and a very weak base. So at equivalence, you're going to have a neutral solution. And then going on beyond then, so this would be 0.2, this would be 0.3. My final point is going to be going beyond a pH of 7. My pH rises at a decreasing rate because now you're fighting against the log scale. Every increase of pH by 1 requires now 10 times more base. So this is just the addition of free moving OH minus. Okay, so that's your titration curve, how you should piece together each of these. For your strong base, strong acid conductivity curve, you start initially high because you have a strong acid which is 100% dissociated, which gives you lots of H plus in solution. That free moving H plus is highly conductive because it's lightweight, which corresponds to this really high conductivity. As you add base, you are reacting that H plus with OH minus, and you're essentially exchanging the H plus for a whatever it is you might be adding an NaOH. you're essentially exchanging H plus for Na plus, which is a much bulkier charge carrier. And so your conductivity starts to decline at a linear rate. Eventually, you hit a conductivity minimum. Why is this conductivity minimum non-zero? That is important to understand. Why is it non-zero? Presence of spectator ions, good. Okay, some of you had preloaded responses to my question. So it's going to have a non-zero pH because we have Na plus, and we also have, if it was say HCl, we would also have Cl minus in solution. Those are still conductive, but they're just less conductive. So it gives you a non-zero equivalence. And the reason why you then start to see an increase going the other way is because there is no longer any H plus. You've neutralized all H plus. From that point onwards, any addition of NaOH is just going to dissociate freely to make Na plus and OH minus, which skyrockets your conductivity up once again. Any questions on those two curves? Okay, continuing on. All you need to recognize in the curves beyond this are the different features in each. So for strong acid, weak base, in a titration of strong acid, weak base, the main difference is just that your pH is lower. And this is because you're making a acidic salt from the weak base. The weak base would make a weak acid, conjugate weak acid, and the strong acid make a conjugate very weak base. Therefore, your pH will be slightly acidic, and that correlates this low pH. The difference in the conductivity curve is you have a slight curved equivalence, and this is due to salt hydrolysis. I won't explain it too much further than that, as most schools don't even mark for it. And then the final ascending portion is because you're adding a weak base, it hardly dissociates. So you're not really adding many ions into solution, and your curve will sort of increase at a very slow rate. Weak acid, strong base is probably the hardest to explain. You have an initial rapid increase in pH or rapid dip in conductivity. And this is because initially in solution, you have H pluses as well as HA. When you initially add OH minus, what's going to happen is you rapidly neutralize all of your free floating H plus. And that's correlating to this initial quick increase. And it will be counteracted by the dissociation of some of the undissociated HA to make H plus and A minus. So this rapid increase at the start is due to the neutralization of a large portion of free floating H plus from the weak acid, which sort of boosts up your pH and drops your conductivity rapidly. From this point, we have a region of the curve, which we call the buffer region. It should make sense now because we've discussed a buffer as any weak acid and its conjugate. In this particular situation, we have a weak acid, which is being neutralized by a strong base, which is why the pH then plateaus out because we've formed a buffer. And the buffer is acting to resist the addition of strong base. And you can see that region in the conductivity curve. Why on earth is conductivity increasing here? Why is it increasing? Exceeds buffer zone, not quite. This is happening as you're neutralizing through the buffer. This correlates directly to this portion of the curve here. This is happening through your buffer. Why is conductivity increasing? Na ions again. Yes, I like that. So essentially, what's happening is as you're adding OH minus, you're adding your strong base, so it's NaOH again. You're going to be neutralizing off your H plus. H plus plus OH minus goes to H2O. So your H plus concentration is still relatively low and it's like slowly decreasing. But as you do this, each time you neutralize an OH minus, you are releasing into solution an Na plus. And so this increase in conductivity in this curve is due to the Na plus concentration rising from the NaOH you're placing in the solution. Every time you place an NaOH in, the OH gets reacted with H plus. The H plus will get replenished, like a large portion of it will get replenished by the equilibrium system. So the HA will redissociate to make more H plus and H2O, not H2O, A minus. And so you're making more Na plus from the NaOH, and you're also making more A minus from the HA, which is driving this rise in conductivity, which is really probably the most unique feature of these curves. You have a curved equivalence again because of this salt hydrolysis, and you have an increase in conductivity as strong base is added because you're adding mobile charge carriers going up. Weak acid, weak base, don't really need to explain, but similar explanation as everything that comes before it. You can figure it out. Okay, those are the only four, only 8 cases that you have. Neutralization models, be able to show neutralization with a MOLYMOD kit. Okay, so now we're on to the big hitting stuff, the very tail end of the module. I can only talk so much in Ka, Kb, pKa, pKb. This comes down to just how many questions you've done at the end of the day. But to refresh everything, Ka, Kb, these are acid-base dissociation constants. High Ka or high Kb means strong, as opposed to low Ka and low Kb meaning weak. We consider the cutoff point for strong and weak to be Ka of greater than 1 being strong, and Ka of less than 1 being weak. Our equations are derived from the dissociation of acid, gives us our Ka expression because it's products over reactants, and for bases, it's just from our base dissociation gives us our Kb. pKa and pKb, literally the same thing. It's just that, like, you can imagine it as a different way of measuring Ka and K, a different way of measuring strength. And it's just a redefined version of Ka and a redefined version of pKa, which makes it more appreciable in terms of smaller numbers. Because if you say you have a Ka of like 10 to the power of 6, it doesn't really mean much to us unless we put it into smaller terms. pKa is equal to negative log of Ka, which once you put it together, you'll have, in this case, a pKa of negative 6 for a 10 to the power of 6 Ka. And the scales for Ka and pKa, as I said, the turning point is around 1. So if your Ka is less than 1, then you are considered weak. And that correlates to a positive pKa. So it kind of gives a nicer measure of strength, where negative pKa means that you're strong and a positive pKa means that you're weak. So they're opposite. One of them will increase as the other decreases, and the turning points are different. Ka is around 1, pKa is around 0. Relating them together, Ka times Kb is equal to Kw, which is 1 times 10 to the negative 14, and pKa plus pKb is also 14. You should be able to negotiate these in your exam. They're not on your formula sheet, but you need to remember these. So typical questions that you'll get is something where they give you a pKa or a Ka, and you're needing to do an icebox to essentially calculate how much will dissociate. Just thinking, should I run through this? We have a few more pages to go. I might not run through it, but the idea is that for this question, you need to change your pKa into Ka. Using your Ka, you can find how much this acid should dissociate. Write out your dissociation of HOCl. Use an icebox, inserting in the starting and end values of concentrations, using X to show the unknowns, and then solve for X using your small change assumption. What's small change assumption? Why does it work? What's our small change assumption? To not have X2 cause the change in concentration is so small, like less than 10 to the power of 3, it changes nothing, doesn't have an impact. It's not so much that we avoid X squared. We can have X squared and still solve, but it avoids a quadratic. That's the main thing. We're avoiding a quadratic, and because chemistry is supposed to be all-inclusive, everyone, even people doing standard maths, are supposed to be able to get a band 6. So you're not meant to be able to use a quadratic to be able to do chemistry. Like, you don't need it. In internal trials and internal papers, they can still get you to do the quadratics. They're not supposed to. So if your school is high achieving and you're planning to get into that high band 6 range, you should still be able to solve a quadratic, but you don't need to. So the small change assumption is essentially, if your Ka is less than 10 to the power of this contentious, because it depends on your concentrations, a safe value is 10 to the negative 5, 10 to the negative 4 some places, 10 to the negative 3 is quite like, it's cutting it fine. 10 to the negative 5 would be a good guarantee of when you're not going to be infringing upon significance. If your K is less than 10 to the negative 5, any change in concentration, say 0.1 minus X, this X would be so small compared to the 0.1, it would be like 0.00005, for example. That X is so insignificant that you're able to say, this X wouldn't change my calculation, and you can cancel it out. And that might look something like this. So this is the solution to that question. You find the Ka, you solve for the Ka expression based on the equation you write. You do an icebox inserting the initial acid concentration and showing changes of X for each, because it's in a 1-to-1-to-1 ratio, giving you end equilibrium concentrations. And you can apply Ka, the small change assumption here, because the Ka expression is significantly small. It is 3.5 times 10 to the negative 8. Therefore, you can essentially get rid of this X from your 0.08 and say that it's so small that it wouldn't affect my calculation, and in truth it wouldn't. So that means you can solve in terms of X squared. X is equal to hydrogen concentration, which is the square root of this, giving you a hydrogen concentration, and plugging that into your pH calculation, you can find pH. So this is your typical question where they give you an acid or base, dissociate, they ask for its pH at the end. Okay. Acid-base analysis. You should know about how you can use titration to find specific concentrations of acids and bases, for example, in the wine industry. And you can use back titration for aspirin purity. So back titration is oftentimes used when whatever you're titrating doesn't react very quickly, and you can't guarantee it'll reach complete reaction from a normal titration. So back titration, you'll react an excess amount of titrant with whatever analyte you're using. So you add in more titrant than you need, guaranteeing that you neutralize all of the acid or base that is present in the analyte. That will leave you with an excess amount of titrant, and you go and titrate this excess, because that allows you to find how much was left over, which allows you to find how much was reacted if you know your initial amount that you added. So this allows you to find this, in combination with this allows you to find this. Okay. There's also the Aboriginal and Torres Strait Islander people acid-base analysis. So you should know that they were able to use clay and ochre as an antacid the same way that we have used it in modern medicine. They can use leaves, neutralize stings, and antiseptic for treating rashes and ringworm. Digital probes and instruments we talked about much earlier, so don't need to double it up here. Finally, buffers in nature. There are three main systems that schools like to talk about. The ocean buffer, which is about carbonic acid making bicarbonate, which then dissociates again into carbonate. The actual buffer is the second part, where it's bicarbonate and carbonate is the buffer. Most of the buffer exists as HCO3. And this buffer works to buffer the ocean. You should have your own write-up of this by now. Acts in the same way as we talked about with buffers before. So you should be able to reason how an addition of acid or addition of base should affect this. So if you added in, for example, base, you could reason that it would decrease my H2O plus, which causes equilibrium to shift right, increasing the H2O plus back up to minimize the change. And that would mean that my pH doesn't change by a significant amount. You could also do it in the same for the second equation. If you added OH minus, it would increase my OH minus, shifting this equation left, which then causes a counteraction. OH minus comes back down. You don't see a big change in pH. That should be what you're trying to get to in your explanation of a buffer. How the system shifts and how pH ultimately doesn't change, because your OH minus and H2O plus concentrations minimally change by the end of it all. The blood buffer and the intracellular buffer, some schools also teach this. I would say as a minimum, memorize one so you can talk about it confidently in a question and understand how buffers work so you can discuss any buffer system through the shifting as we've done today. Finally, the tough calculation is one of the tougher types is a buffer calculation. If you haven't seen it before, you would get decked by it in your exam, but you've seen it here. So a buffer calculation is where you have a buffer, which is a weak acid and its conjugate in solution. They tell you the concentration of both of these, and they tell you what the Ka is, and they ask you to find the pH of this buffer, because at some point, this acetate and acetic acid will reach equilibrium. So the first thing you need to do is write out the equation, including these two, this acid and its conjugate base. In this case, I've given it. So you need to find the Ka. To find the pH at equivalence, or at equilibrium rather, you need to find the concentrations of each part in terms of X. If you start with 0.0625 of acetic acid, you show that as the initial. So this initial column, to be really clear in your icebox, you imagine it as your acid and base before anything has dissociated. That's your initial. Your acid and base before anything dissociates. So they're your acetic acid and acetate before anything's changed. And your hydronium concentration will be 0 because you're assuming that nothing has dissociated yet. You've just added in these exact concentrations of acetic acid and acetate together. Before I move on, why has everything halved? Really important step, because this will throw everything off if you don't do it. Why has everything halved? Why have both the concentrations halved? Good. 2 liters of solution. Always consider when you're combining solutions together, you have to consider the volume change. And that's why our initials are half of what the question stem provides. Be very careful. The changes would be a shift to the right. Since you have absolutely no hydronium, the system has to shift right. The system at the moment is very far to the left, so it wants to go right. Therefore, you're going to dissociate acetic acid, make acetate, and make hydronium. You show those changes, it should be minus X. And you solve from there. Because you have, once again, a Ka that is significantly small, this is probably like borderline 1.76 times 10 to negative 5. You can probably get away with it here, saying 10 to negative 4 is just negligible. you can get rid of the x's, which allows you to solve in terms of x, and you can find that x is equal to 8.8 times 10 to the negative 6, allowing you to calculate pH based on that concentration, which gives you 5.055609 or 5.056 to 3 decimal places as per the question stem. And that's pretty much as bad as your calculations should get. That being said, they're getting harder. I know that as a fact. Take, for example, the 2021 double back titration. I gave all my students that in term 1. That was a hellish question, but a really nice calculation. Everyone asks about Henderson-Hasselbalch. You don't need to know it, but if they give it in the question, you need to know how to use it. So pH is pKa plus log of A minus and HA. Just keep it handy. You don't really need to know it. And here's some other buffer calculations if you want to try. I'd say these are high yield. And that's it. That's all of Module 6. We've gone quick. Hopefully that refreshes everything for you. And if there's any more questions, I'll stick around for a bit after the session to answer them. But I don't want to take up any more of your evening if you've got other things to study, as I know most of you have exams in a week or two. If you found this useful, the session will be up online for you to review, but also this is what we do during the term. So we did this with our students about a term and a half ago now, and they did this 3-4 weeks ahead of everyone else at their schools. And that's what helps us to get results like our students scoring first, second, or third in their cohort. Every 1 in 4 does that. So if you're interested and you found this helpful, we do offer tutoring. We start July 1st, this coming holidays. And for the year 12s, we'll be finishing module 8 before the end of the holiday. So that would mean that you start your term, step forward in the class without having any more content left to cover. And you're just doing questions from there. You're able to do every single HSC question from week 1 of term 3. So if you would like to hear more about it, send us a message on Instagram or TikTok, or even on our website. You can submit a form, and we'd love to help you get to that mark, whatever you're dreaming of, whether it's a band 6, a higher range band 5, or wherever you want to go, we can help you get there. In terms of whether you get access to this booklet, unfortunately not. This is only for our students, but there will be a recording online with this whole session, so you can access the pages through there, but the PDF itself won't be shared. And that's pretty much it. Enjoy the rest of your evening. As I said, I'll stick around for some questions, but other than that, see you around. Hopefully it was helpful. That's all that we needed. The recording will be up on YouTube. So it'll be on our YouTube channel, titled something like Module 6 Speed Run Rapid Review, something like that.